Okay, here's a more difficult power problem that you might have to solve. But actually, this is attached to a homework problem you do have to solve. And here we have a ski tow that operates on a hill, a slope of angle 14.3 degrees. And it has a length of 350 meters. The rope moves at a speed of 12.1 kilometers per hour and provides power for 49 riders at one time, with an average mass of 75 kilograms. And for now, we're going to assume friction is negligible, so it's pretty easy. And we have to estimate the power provided by to operate that tow. So there's a picture. These are tubers being pulled by a tow rope, so you have an idea what's going on. Now, power, there's a lot of ways to figure out power. But here we know velocity, it's constant, so there's not really a change in kinetic energy. There's a change in potential energy, but that seems like it'd be a lot to figure out. So I think the best way is going to be power is force times velocity. And I just need to find the force that is exerted by the tow rope. So let's draw a free body diagram. Now it says there's 49 riders, average mass of 75. I'm just going to treat them as it's one person with all that mass. There's a tension from the tow rope up the ramp. There's gravity straight down. There's a normal force perpendicular. Now it says we're going to say friction's negligible, so we don't have to worry about any friction in this case. And the acceleration is 0 because they're moving. It doesn't say a constant speed, but it doesn't say they're speeding up or slowing down, so we have to assume it's constant. All right, I need to find that force. And that's the force that's in line with the velocity. This force must be in line with that velocity because of work, and the force has to be in line with the displacement. So let's choose an axis. The force we need is that tension, so we'll choose an axis that lines up with the tension. And if you recall, this angle here of the hill is the same as this angle right here between the gravity, which is vertical, and the y-axis that's perpendicular to the slope. So if we add up the forces in the x direction, they'll equal max, which is 0, and we know it's tension minus mgx. So the tension is going to equal mgx, and that equals mg sine of the angle of the slope. And there we go. We have our force. So it works out to not be that difficult. The power is going to be mg sine theta, that's the force, times the velocity. We do have an issue here that this velocity is in kilometers per hour, and I got to convert it to meters per second. But we'll plug all those numbers in along with the conversion and see what we get. So this power is, the mass now, 75 kilograms per person, but there's 49 people. So that's 75 times 49 times g is 9.8 times the sine of 14.3, all that times that velocity of 12.1 kilometers per hour, but that has 1,000 meters for 1 kilometer, and 1 hour is 3,600 seconds. I can reduce this and this and plug all that in. So we're going to do 75 times 49. That's a times, right? That's multiplied by, not a decimal, likewise there, times 9.8 times the sine of 14.3 times 12.1 times 10 divided by 36. Ka-chink. 29,899. So that power is 29,000. What do I have? 2 significant digits. If I go to 3, 29,900 watts, which would be 29.9 kilowatts. And done. There we go.